Hello everyone and welcome to 8.1 Energy Sources, video 1 of 4. So as usual, I like to start with this slide right here because it has all the formulas. So for example, power is energy divided by time, and well, this other formula which we'll see. I just want to switch screens here for a bit. Okay, so if you can take out your formula booklet, always have this out when you're going through the lesson. You're looking in box 8.1, so that is at the bottom of page 7. So box 8.1, energy sources, sure enough, those two formulas are right there. Okay, so we're going to see the first one today. And of course, actually, power is equal to energy over time. You've seen that formula before. You've seen it in grade 11, but now at least you know where to find it. We're not going to get to the second formula today, but we will get there in this section. Okay. Going back to the slides. Okay, so we're just going to pass through that. All right, primary energy sources. Something that I just want to point out is that in this topic, this is a very interesting unit. So while the previous unit did, and also the one before that, had a lot of calculations and there was application to it, this one is even heavier in application, but it still has a lot of calculations as well. So just something to keep in mind. All right, so we're going to start off with some conceptual knowledge. Okay, so a primary energy source. If there is some kind of energy source the consumer uses directly, this is considered to be primary. So for example, if a person places wood in a stove and produces heat, and they use the heat directly, this is considered a primary energy source. Or if a person uses a water wheel and they use the mechanical energy from the water wheel to grind wheat into flour, that's another use of energy that's considered primary. Okay, so here are some examples of primary energy sources, and these are the relevant percentages. What you'll notice in these pie charts is that solar energy is huge. Okay? You've got wind energy at 27%, geothermal at 17%, and biomass at 12%. So we'll talk a little bit more about what biomass is in the next few slides. Now, notice that this big chunk is really just 2% of this other big pie chart. Okay, so all of these are all the various energy sources. So we've got oil. Oil accounts for 38% of our energy use. Natural gas, we've got coal, we've got hydroelectric, that's water, and you've got nuclear. So that other 2%, that's, if you notice, this is essentially renewable, right? So solar, wind, geothermal, biomass, all of these are renewable except actually biomass. So biomass is, well, eventually fossil fuel, so we can't actually reuse that. Okay. Describe the origin of fossil fuels. All right, so understanding this, if you studied biology, I mean, you're going to be a whiz at this. This probably was covered in earlier science courses as well, but still we're going to go through it step by step. Okay, so the first step is that the sun makes biomass through photosynthesis. Let me break that down. Okay, so biomass essentially means that the object, the organism, is gaining size. And photosynthesis, well, that's the process that many organisms use to convert sunlight into usable energy. Okay, so biomass is organic matter. Photosynthesis, well, plants and animals get energy from the sun and, well, they convert it to their own chemical energy. Okay, biomass gathers and grows over time. All right, so putting these two together, imagine you have some kind of a plant. You put it in some soil, you got some seed, you put it in soil, you add water to it, and you need sunlight. So the combination of water and sunlight allows this plant to grow, and it grows bigger, so it accumulates biomass. Okay, that's why we say it grows over time through photosynthesis. Okay, biomass buried under great pressure and heat. And so once the organism dies, whether it's a plant or an animal, well, it's going to be eventually covered by any kind of material, right? Like some kind of dirt or some kind of sand, and over time that creates a lot of pressure. Now, all that pressure and heat, now keep in mind this is happening over a time span of millions of years, this becomes coal, oil, and or natural gas. Right? Now, how do we get coal? Well, coal is coming from plants. So if you have plants on land, coal is a solid substance. Oil, on the other hand, that's liquid. So when you have marine organisms, so underwater organisms, when they are deposited on the seafloor, eventually this will become oil. Now, natural gas, as you might expect, that's gas. Okay, so you've got solid, liquid, and gas. This is also from the remains of marine organisms, but they're at really large depths inside of the earth. So we have to drill for it. Okay, all three of these are used as fuels. Okay, so coal, a lot of countries, and even us, we use coal as part of our total energy production. Oil, well, you're using oil in your car when you're coming to work or you're coming to school. Natural gas, that's what's used to heat up your homes. So that's what's used to heat up your hot water boiler most likely. It's what's used to power your furnace. Okay. So what's the big difference here between biomass and fossil fuel? Well, it's just the amount of time. Biomass is when the organism is alive, and fossil fuel is after it's been dead for millions and millions of years. So the big difference between biomass and fossil fuel is time. And, well, quite a bit of time if you want to get specific. Okay, so let's take a look at this. Proved reserves. These are resources that we are sure we can obtain. Production means actual reserves that have been obtained and placed on the market. So this is data from 2005. We have to use this data to figure out how long reserves might last. Okay, so let's see here. Coal. This is all in 10 to the 9 tons. In 2005, we knew that we had about 909.1 times 10 to the 9 tons of coal. So that means we know that it exists, that we can obtain it. And in 2005, 5.85 times 10 to the 9 tons were used. And of course, we've got the same in oil and gas. Now, the question wants us to estimate how long oil reserves might last. Well, if you have 1200.7 times 10 to the 9, right, for oil, this is the total amount of capacity you have. And in 1 year, you're using 29.6, well, whatever unit of mass that is. So it looks like it's in barrels. Well, you can figure out how many years there's going to be. So this is actually a pretty straightforward calculation. Just take the total amount you have divided by how much you're using per year, and you're going to get the number of years. So that's about 40.6. Now, keep in mind that this number is subject to fluctuation. Right? So this is a number in 2005. We're in 2020 right now. So a lot of things have changed. More people are driving more cars. There are more factories, although some of them are a little bit more efficient. So this number is fluctuating. This is a rough estimate. Okay. So this image is actually very interesting to look at. So there's a lot of information here right now. We've got different continents and different areas around the world. So we've got North America, South and Central America, Europe and Eurasia, Middle East, Africa, Asia Pacific. And just notice the breakdown of what types of energy they use. Okay, so just take a moment to look at that. Pause the video if you'd like. Okay, so what we notice is that, well, every country is using oil, every country uses natural gas, every country uses coal, every country uses hydroelectricity, although in varying amounts. Okay, so we more or less use the same amount of oil. And what we notice is that with nuclear energy, okay, so North America does use a lot of nuclear energy. Europe and Eurasia also use a lot. The other areas in the world, not so much. And in fact, in the Middle East, it looks like there's almost none, although there is a little bit. Okay, so this is data from 2009. So of course, that's been updated now. We notice in South and Central America, there's a lot of hydroelectricity, a lot of energy from water use. It's something interesting to notice is that coal is still so abundant. We use a lot of coal in North America. They use a lot of coal in Asia Pacific. Almost no coal in the Middle East, although they use a lot of oil. Okay, so we're going to look at the efficiencies of using all of these different types of fuels: coal, hydroelectricity, nuclear energy, natural gas, oil. Okay, so how much energy does each kilogram of these types of fuels have? How efficient is it to use? But then we also have to think about, well, what kind of waste is generated or what kind of pollution, right? All of those are questions that need to be asked. Okay, so we talked about primary energy sources on the first slide. Now let's look at secondary energy sources. Okay, so a secondary energy source electricity, hydrogen, something that has been transformed from a primary energy source before used by the consumer. Okay, so for example, electrical power lines. Right? So the consumer is using the electricity, but I mean, where did the electricity come from? Right? So we're actually going to be studying that quite a bit as well later on. But this is considered a secondary energy source. All right, now, if you've noticed, there are a lot of buses that run on natural gas. Okay, so something that cities and countries are moving towards is using hydrogen as a fuel source. Okay, so instead of just having, well, electricity or gasoline or natural gas, we have hydrogen. Okay, so you have a hydrogen fuel cell. And the idea is that when you combine hydrogen with oxygen, your outputs are just electricity and water vapor. So if water vapor is your only byproduct, I mean, that's a pretty clean system. Hydrogen fuel cells are a little bit difficult to create. Okay, so we'll look at this a little bit more in detail, but for now, I'm going to move on to the next slide. All right, so this is how we're going to compare different types of fuel sources. There's two things you can look at. There's specific energy and there's energy density. So specific energy just means how many joules of energy can you get for every kilogram of that fuel. Right, so if you get more joules per kilogram, that's exactly what you want. Energy density is how much energy you have per unit volume, right? So mass and volume are not the same thing. So you can have something that's very dense and very compact, right? In which case, well, you would have more energy stored. All right, so let's give this sample problem a try. Fission of uranium-235. So in grade 11 physics, we learned about how nuclear power is generated, and we're going to study that in a lot more detail in this unit. Okay, so we saw that when you have fission, okay, so fission means splitting of the atom. Okay, so you have a very heavy atom here. You split heavy atoms to release energy. For low mass atoms like hydrogen, helium, carbon, they undergo fusion. Fusion is when they merge together, and that also releases energy. Okay, but again, for uranium-235, that's very heavy. They undergo fission, they split. Okay, so fission of each uranium-235 produces 3.5 times 10 to the minus 11 joules of energy. The density of uranium-235 is 1.8 times 10 to the 4 kilograms per cubic meter. Calculate the specific energy and the energy density of uranium-235. Okay, so I'm going to switch to paper mode here. So hopefully you have the slides in front of you if you printed them out already. So we're trying to figure out the specific energy, so ESP, for uranium, and we also have to figure out the energy density. Now we're dealing here with uranium-235. Now if we revisit the definition of specific energy, it's how many joules you get per kilogram. Okay, so we want to know how many joules we get, well, for one atom of uranium-235. But for uranium-235, well, I got to know what the mass is, right? So to figure out the mass of uranium-235, you have to remember how something like this is written and why it's written the way it is. When you have the element symbol with a dash and the number, this number here is the mass number. Okay, so the mass number tells you how many protons and neutrons, or how many nucleons, are inside the nucleus, right? So nucleons are things like protons, neutrons, okay? When you're trying to figure out collectively what you have here, since I don't have a periodic table, I don't have the number of protons for uranium, I only know I have 235 nucleons. So that means the mass of uranium-235 is 235 atomic mass units. Okay, so that's what that U is here. Atomic mass units. So this is an overall approximation of what you can approximate the mass of a nucleon as. So what you need to do now is take out your formula booklet. So you should already have it. So in your formula booklet, you're going to turn to the page of constants. Okay, so in your page of constants, near the bottom, the third item from the bottom is U. Okay, let me see if I can actually get that in focus here. Okay, so if you see U, the value for U is about 1.6, it's not focusing
unfortunately, but it's there, 1.661 times 10 to the minus 27 kilograms. Okay, so I have 235U times, well, 1U is 1.661 times 10 to the minus 27 kilograms. So that when my units cancel, I'm left with
kilograms. All right, so then my U's are canceling. All right, so let's grab our calculator and figure out what this is equal to. So 235 times 1.661 times 10 to the minus 27. Okay, so the mass of uranium-235 for one atom is about 3.9 times 10 to the minus 25 kilograms. Okay, so we've got that. Now, to figure out the specific energy, well, if you recall in the question, let me actually just pop over there for a second. In the question, we're told that each uranium atom of 235 produces 3.5 times 10 to the minus 11 joules of energy. Okay, so let's go back here. So we have 3.5 times 10 to the minus 11 joules of energy, right? Now, if we take that and we divide by, well, how many kilograms do we have for one uranium atom, that's 3.9 times 10 to the minus 25 kilograms. Well, I'm going to have how many joules per kilogram I have for one atom of uranium-235, and that's exactly what I want. So I'm going to go ahead and divide these two numbers. So I've got 3.5 times 10 to the minus 11 divided by 3.9 times 10 to the minus 25. I've got, well, it's about, let's round that to 9. So that's about 9 times 10 to the 13 joules per kilogram. So every kilogram of uranium-235 has that many joules. That's a lot of energy. That's a lot. Okay, so later we're going to see, compare that to coal. We're going to compare it to wind, solar. This is a lot of energy. Okay, so this is the specific energy for one atom of uranium-235. Okay, so that's part A. Now, part B, so it's not actually divided into A and B in the question, but this is the first and second part of the problem. We have to find the energy density. And now, if you remember, energy density is the amount of energy per unit volume. And so if I go back to the question, I'm told that the density of uranium-235 is 1.8 times 10 to the 4 kilograms per cubic meter. I really need to use that value, so let's use it. 1.8 times 10 to the 4 kilograms per cubic meter. Okay, so how does that help me? Well, I know that I need joules per cubic meter, right? And here I have joules per kilogram. So if I multiply these two values together, so 9 times 10 to the 13 joules per kilogram, well, guess what? My kilograms are going to cancel, and I'm going to be left with joules per cubic meter. And again, that's for one atom of uranium-235. So that's exactly what you want. Okay, so multiplying these two numbers together, 1.8 times 10 to the 4 times 9 times 10 to the 13, 1.62 times 10 to the 18. And that is joules per cubic meter. So that's the energy density. Okay. Now, if you're feeling a little bit uncomfortable with this question because we didn't use formal formulas and equations, we were just trying to figure this out based on the information given, that's unfortunately something you're going to have to get used to in this unit. You have to be able to solve these kinds of problems given information, but not necessarily being able to use the formulas. Okay, so I knew that each atom of uranium-235 has this mass, and I know that this amount of energy is coming out for one fission reaction, so I can figure out the energy per unit kilogram. Right? So likewise, using that information for one uranium-235 atom, I can figure out the energy density of one atom. Okay, so given its density. Hopefully that's okay. So we're going to go back to the slides now. Okay. Now, most of our energy does come from fuels. Okay, so let's look at some values and compare them. Okay, so petrol. Petrol is also known as gasoline. So the specific energy for petrol is 46.9 megajoules per kilogram. Now, if you remember, what we just saw was that for nuclear energy, we had 9 times 10 to the 13 joules per kilogram. Now, if you want to change that to megajoules, that's fine. You just have to take 6 away from the exponent of 10. So that becomes 9 times 10 to the 7 megajoules per kilogram. So that value is going to come up on this table as well. Huge difference. Okay, diesel. Diesel is also a fossil fuel, 45.8, so just a little bit less than gasoline. Biodiesel. Biodiesel is just a more eco-friendly version of diesel. There's less sulfur in it, so less harmful to the environment. We have crude oil coming in at 41.9 megajoules per kilogram. There's coal. Coal is really inefficient. Okay, there's a lot of coal, but it doesn't output much energy. From each kilogram, we only have 32.5 megajoules of energy coming out. And you compare that to sugar. Okay, if you double sugar, you have just as much, actually more, energy output compared to coal. Okay, wood. Wood's about the same as sugar. Cow dung, 15.5, and household waste, 10. Okay, so you can see at the top of this list, we have gasoline and diesel. So they're producing quite a bit of energy per unit kilogram. But the reason why the first two rows were left out is, well, once you look at these numbers, it's just going to blow you away. Okay, so if you look at uranium-235, okay, this is a nuclear fuel. Okay, every kilogram of nuclear fuel produces 90 million megajoules. Okay, so that's another 6 zeros on the end of this, joules per kilogram of that fuel type. If you look at gasoline, it's only at 47. Compare 47 to 90 million. That's a huge difference. Okay, so nuclear fuel is so much more efficient and takes up a lot less space. Although there is also drawbacks of nuclear fuel. There is the waste, which we'll get to. If you split a proton, that's huge. You're going to get 300 million megajoules per kilogram. Now, splitting a proton requires a lot of energy currently. That's not something we could easily do. But uranium-235, we can do that very easily. Okay, let's keep going. All right, renewable and non-renewable energy sources. Okay, so we talked about this in the beginning, but let's actually talk about, well, what does it mean to have a renewable source? Renewable means that the energy source can be replenished in our lifetime. Okay, so when we say that the sun is a renewable source of energy, you know that the sun is going to burn out in 4.5 billion years, but in the human lifespan, it is renewable. Right? So we know that nothing actually lasts forever, but within our lifespan, if it lasts long enough, it's considered renewable, right? If it's able to regenerate itself as fast as we use it, that's considered renewable. Okay, so we have different kinds of fuels here from the sun, and well, these are not fuels, also helping from the sun. Fuels, so coal, that's not renewable. Oil is not renewable. Gas is not renewable, but wood and biomass, they are renewable. Okay, solar energy, hydroelectric. Okay, so well, this solar energy, that's energy from the sun. Hydroelectric, that's water, right? So if you have a dam, right? Wind energy, well, that's self-explanatory. Waves, you can also generate energy from that. Photovoltaic, okay, this is a solar cell, okay? So like a solar panel. Okay, so this is renewable because solar energy is renewable. Non-sun derived energy sources. Okay, so hydrogen, uranium, and chemical, none of them are renewable. Once you use up, for example, uranium, you have radioactive byproducts. You cannot break those down again. Non-fuels, tidal, geothermal, and chemical. Okay, so tidal and geothermal, they are renewable. Geothermal, that's heat coming from inside of the earth. Okay. All right. So this slide essentially goes to the point that, well, renewable is better than non-renewable because it's not going to run out, right? So we use it at a certain rate, but it replenishes itself at the same or greater rate. So why not just use renewable energy? Well, unfortunately, it doesn't produce enough energy to meet our needs based on what we have right now, based on our current systems. Okay, so let's see. Oil and gas are better than coal because they burn more efficiently and produce less carbon dioxide. Coal is cheaper and more plentiful than gas and oil. That's true. We have a lot of coal. Now, nuclear power is advantageous because it doesn't have pollution. There's no byproducts in that sense. It does have nuclear waste, however. Okay. Hydroelectric systems are useful because they can store extra energy. Okay, that's why you have dams. The dams hold that water in place at a high elevation until they are required to be used. Okay, burning biomass alleviates landfills. Well, that's true, but that's also going to contribute something to the atmosphere. Nuclear waste lasts for thousands of years. Okay, so if you break down uranium-235 and one of your byproducts is radioactive krypton, well, you're going to have to let that sit for a while in a safe area until the radiation from its half-life decay is complete and it's more stable. All right, wind turbines and photovoltaic cells depend on the weather conditions and have small output. Okay, so places in North America, or let's say Canada actually, in Canada it's a little bit harder to have solar panels because we have a lot of cloud cover. It's not as sunny as it would be in a place like Florida, where a lot of people have solar panels. And the other thing with wind turbines is that they take up a lot of space. So if you've ever entered the Canada-US border from Windsor, you would have driven by these large acres of land filled with wind turbines. So that's not something you usually see in a city. Okay, so let's actually solve an energy density problem. All right, so coal has a specific energy of 32.5 megajoules per kilogram. A coal-fired power plant that needs to produce 30 megawatts of power, so that's for a city, and it has an efficiency of 25%. How many kilograms of coal are needed daily? All right. So we're given quite a bit of information in this question, so let's see what we can work with here. So again, hopefully you have the slides in front of you. If not, maybe take a screenshot of this, take a picture, so you can constantly refer back to the question as we work through the solution. Okay, so we're dealing with coal here. Okay, so coal has a specific energy, so ESP, of 32.5 megajoules per kilogram. Okay, if a city has a coal-fired power plant that needs to produce 30.0 megawatts of power, so P is equal to 30.0 megawatts, with an efficiency, so the percent efficiency is 25%, how many kilograms of coal are needed daily? So if we're looking for how many kilograms, that means we're looking for mass. Okay, needed daily, well, that's telling you the time frame. Okay, if the time frame is daily, that means you're looking at 24 hours. Now, before we can use that value in a question, as you know, I have to convert that to seconds because I need to only plug in SI units into these kinds of formulas. Okay. Now, percent efficiency, not something that we've really looked at so far this year, but right now, this is something you got to just use your common sense for. If a city needs 30 megawatts of power and the plant is only 25% efficient, think about that. That means the plant has to produce more than 30 megawatts of power so that when that extra power is lost due to inefficient means, due to resistance, or it's lost due to any other sort of means that is not what it was intended for, after it loses that energy, you're down to 25% of what it was, which is 30 megawatts. Okay, so if 30 megawatts is 25% of some bigger number, well, what's that bigger number? Okay, so it's just going to be 4 times 30. Okay, so if I have 120 megawatts, okay, so imagine you have 12. What's 25% or what's 1/4 of 12? Right? It's 3, right? So or 1/4 of 120 is 30. Okay, so if I have the plant producing 120 megawatts of power, but the plant's only 25% efficient, which means whatever energy I put in, only 1/4, only 25% that comes out is useful. Well, that's 30 megawatts. Okay, so this is what I need to produce. Okay, so you have to produce 120 megawatts. Now, that is a power. Power is always measured in watts, so here we have megawatts. 1 watt is 1 joule per second. So 120 megawatts, that's 120 joules every second. Now, to figure out how much energy this plant needs to produce per day, I have to multiply by the number of seconds in a day. That way I get how many joules I have. Well, I know in one day I have 24 hours. Now, in earlier videos, we converted 24 hours to seconds, but I'm going to just do it from scratch here so you see it. So 24 hours multiplied by 1. Okay, so 1 hour is 60 minutes, multiply by 1 again. 1 minute is 60 seconds. Okay, so hours cancels with hours, minutes cancels with minutes, and you're left with seconds. So 24 times 60 times 60, and we get 86,400. And this is what I was saying earlier. The more you do these types of questions, this number is going to sound more and more familiar to you. Hopefully it is already sounding familiar to you. Okay, so we have 86,400 seconds in a day, and the plant is producing 120, well, that should be megajoules of energy per second. So multiplying that by 86,400 seconds, let's see what we get. I'm going to keep this in megajoules, right? Because my seconds are going to cancel. So 120 times 86,400, that's a pretty big number. All right, so we've got 1.037 approximately times 10 to the 367. Okay, so that's 1.037 times 10 to the 7 megajoules. Okay, so just keep track of your exponent, keep track of your prefix. So if you want to change that to joules, you add another 6 to the exponent here, making it times 10 to the 13. But actually don't do that right now because our specific energy is also in megajoules. Okay, so this is how much energy we have to produce. And I know that each kilogram of coal will produce 32.5 megajoules of energy. So I need this much, and I know that each kilogram provides me this much. So dividing these two numbers by each other, I will get the number of kilograms. So the number of kilograms of coal is going to be, well, I've got 1.037 times 10 to the 7 megajoules of energy that I need divided by 32.5 megajoules per kilogram. Okay, so this way my megajoules cancel out, and I'm going to have, well, if you actually work out these units, here you have effectively 1 over 1, and here you have 1 over kilograms. This works out to be kilograms, right? So when you divide two fractions, you multiply by the reciprocal. Well, you guys are in grade 12 now. I'm sure you can figure out that the units coming out here are kilograms, okay? So let's go ahead and do our calculation here, see how many kilograms of coal we need. 1.037 times 10 to the 7 divided by 32.5. And we have 319,076.9 approximately. So if we want to use sig figs, well, we have percent efficiency 25%. That usually doesn't factor into sig figs here. We have about 319,000 kilograms of coal. And if you want to round that to 2 sig figs, that's fine as well. So we have 320,000 kilograms. That's a lot. Okay, so for one city, you know, assume this is an average size city, you need a coal-fired power plant. This is how much coal you need per day. That's a lot of coal. All right, so on the next slide, we're going to actually really bring this idea home. Okay, so let's go back to the slides now. All right. If coal is transported in rail cars having a capacity of 1.5 metric tons, how many cars per day must supply the power plant of the previous example? Okay, yeah, just kind of look at that picture, let it sink in, all right? So each one of those rail cars is carrying coal. We just saw that we need 319,000, almost 320,000 kilograms of coal per day. And I know that each rail car has a capacity of 1.5 metric tons. Now, a metric ton is not the same thing as a ton. Okay, so I'm going to go back here to the page. I know that I have about this much mass in total, and each rail car can hold 1.5 metric tons. Now, this is not something that you need to remember. If you do need to know it, I will give you the conversion, but 1.5 metric tons, a metric ton is 1,000 kilograms. Okay, so if I have 1.5 metric tons, I know tons can be spelled two different ways. I actually don't know the difference, but here we go. It's 1,000 kilograms per metric ton. Okay, so these cancel and you're left with kilograms. Okay, so you can do that math in your head. 1.5 times 1,000, that's 1,500 kilograms. So each rail car can hold 1,500 kilograms of coal, and we need 319,000 kilograms in total. So the number of cars is going to be the total mass that you have, which is 319,000, divided by how much each car can hold, which is 1,500. So 319,000 kilograms divided by 1,500 kilograms per car is equal to, let's see, that's about 213 cars. And that's rail cars, by the way. That's a lot. Okay, so going back to the picture, so we've got 213. Going back to the slide here, imagine 213 of these rail cars per day per city. That's a lot. Okay, so the reason, first of all, there's a couple of reasons why you don't see that. One of them being, well, not every city produces its own electricity. Okay, so cities and countries buy electricity from other places. Not to mention, coal is not the only source of electricity, well, that we use in Canada or any country for that matter. It's a combination of coal, oil, solar, wind, nuclear. Okay? There's a lot of different sources. But if we were just using coal, this is how much it would take per day. So it's just a bit of an eye-opener there. Okay, so let's move on to the next slide. Okay, if a nuclear power plant powered by uranium-235 has the same output and the same efficiency as the coal-fired plant of the previous example, how many kilograms of nuclear fuel will it burn per day and per year? Okay, so we're assuming it has the same efficiency and the same output. So let's go back to, well, our paper here. Okay, so what we found was from the first example, the power plant has to produce this much energy. Now, however it produces it, whether it's coal, nuclear, wind, solar, it has to make this much, right? It has to make 1.037 times 10 to the 7 megajoules of energy so that the city can run. So if you're using nuclear fuel now, well, if you remember in our first example, not this one, but earlier, and also in the table that you saw, we looked at the fact that each kilogram of nuclear fuel, well, produces 9 times 10 to the 7 megajoules of energy. So if you have to pause the video and go back to that table, just take a moment and do that. Okay, so let's actually work this out. Okay, so we've got, so let me just write this number down again. So we need 1.037 times 10 to the 7 megajoules of energy. So 1.037 times 10 to the 7 megajoules of energy needed. Okay? And for nuclear fuel, actually, let me just move this out of the way. For nuclear fuel, I've got, so again from the table, it's 90 million megajoules per kilogram. That's 9 times 10 to the 7 megajoules per kilogram. Okay, so that means megajoules are going to cancel and I'm going to be left with kilograms. So 1.037 times 10 to the 7 divided by 9 times 10 to the 7. Now, those of you that are very keen in math, you probably noticed that I have 10 to the 7 on top, 10 to the 7 on the bottom. Those can technically cancel as well. So I really just have to do 1.037 divided by 9, and I'll get the same value here. Okay, but overall, we get 0.115, approximately 0.115 kilograms. Okay, I really want you to sit with that piece of information. We found in the second previous example that it took 320,000, approximately 320,000 kilograms of coal to power that city. And it's taking about 115 grams of nuclear fuel to do the same thing. So if that table of specific energy of various fuels, of nuclear versus coal, didn't put that into perspective for you, I think this really will. 320,000 kilograms versus 115 grams. Okay, so that's per day, by the way. Okay, so 115 grams per day. So if we want to convert that to per year, well, I have 365 days in a year. So if I have 115 grams per day and I multiply that by 365 days in a year, well, I'll get how many grams I have per year. So, well, this will be kilograms if I use the same number that's on my calculator right now. So times 365. So that's 42 kilograms approximately. Not too bad. So for 1 year, you would use 42 kilograms of nuclear fuel to power this city, as opposed to 320,000 kilograms of coal for 1 day. So quite a big difference there. All right, so let's go back to the slides. All right, explain why it is advantageous to have a submarine which is nuclear powered as opposed to diesel. All right, so, well, we just saw one big reason. You don't need as much nuclear fuel as you would other fuels because it is so much more higher in energy output per unit mass. Okay, so, well, that's one thing. You don't have to carry oxygen tanks underwater. So there's a few pieces here. Okay, there's going to be less mass on board. Less space taken up, and less stops to fill up on fuel. So the submarine can actually travel longer compared to before. And so all of that is written in the slides here. Okay. Sankey diagram. So notice that the heading has now changed. Okay, so we're going to be looking at what a Sankey diagram is today and in the next video as well. So consider the following scenario. Okay, so you have some kind of open flame. Okay, so there are a lot of energy transformations that take place as this fire is produced. Okay, so there is some kind of chemical reaction that produces heat energy. So the chemical energy stored in either the wood or coal or whatever you have. Okay, so let's say wood or fuel, let it be kerosene or whatever you kind of fuel you're using. That chemical energy gets converted to thermal energy, right? So you might use that thermal energy to cook something, you might use it for warmth, okay? But overall, you have a conversion of energy from one type to another. Now, something that we've been studying in physics last year and this year is conservation of energy. We said that the total energy in a system always has to stay the same. Energy cannot be created or destroyed, it can only change forms. And sometimes when it changes forms, it might change into the right form you want, but it's not used efficiently. So that's what we have to look at here as well. Okay? Sometimes heat is lost to the environment, or it's just wasted. It doesn't disappear, but it's not used as it was intended. So let's move on to the next slide now. All right, so we're going to use an example of a hot air balloon, right? So we've got fire. Okay, so a little bit of a flame underneath the hot air balloon is what allows it to rise. Okay, now, if you want energy, or in this case the heat, to be converted to useful work, you need some kind of an engine. Okay, an engine is some kind of a device that converts energy from one form to another form. Okay, specifically, an engine is a machine that turns energy into mechanical force or motion. Okay, so usually you have some kind of fuel burning. Now, we can do the same thing with a hot air balloon. We can treat the hot air balloon as an engine. Now, it's a very simplified engine, definitely not the same kind of engine you find in your car, but it's still a type of engine. It's still turning energy into a mechanical force or motion, and we'll show you how that's done. Okay, so we are going to make an electricity producing engine using the hot air balloon. All right, so how do we do that? Notice that now in the animation, attached to the bottom of the hot air balloon is this blue oval. Okay, so imagine this is some kind of sack of water. Now, when the hot air balloon is at a certain height, a hole is punctured inside the water, inside the water sac. So this water starts to fall down. Now, being at whatever height it's at, there's gravitational potential energy stored inside the water. So as it falls, it gains kinetic energy. Okay, so imagine now at the bottom of the stream of water, we place a fan. And the water stream hits the blades of that fan at exactly the right angle to cause it to turn and rotate. Okay, so the rotation of these fan blades is now generating electricity. Okay, so now we have an electricity producing engine. And the idea is, well, once the water runs out of the sac, now we have to cool down the air inside the balloon, right? So you have to reduce the flame, cool the air inside so this system comes back down, we refill the water, and then we turn on the heat, and the whole process continues. So the idea is there has to be a cyclical process, so a process that continues to repeat itself. So heat up the air, balloon goes up, water starts pouring down, makes the fans turn, after which this has to now cool down, right? So the balloon cools down, comes back down, refill the water, and then go back up again. So the system continues to repeat itself. Okay. In the balloon water electricity engine, name all of the energy conversions that occur. Okay, I'm sure you can think of quite a few right off the top of your head. Okay. So, first thing, either you have coal or wood to become heat, or you might even have some kind of oil. Okay, so you have heat generated. Heat expands the air in the balloon, right? So that's how the balloon is able to go off, right? So you have the air inside the balloon getting warmer, and that air is warmer than the air surrounding the outside of the balloon. Since the air inside is warmer, the particles move away from each other, creating a less dense fluid inside of the balloon. Okay, so according to buoyancy, if you have something of low density, it will rise higher than objects of higher density. Right? So if you pour oil with water and you try to mix it, the oil will always sit on the top because it is less dense than the water. Okay? It's the same idea. So that's what makes the hot air balloon go up. Okay, so that's heat. The buoyant force, so that's what I was just discussing. It causes the balloon to rise, increasing the potential energy of the water, right? Because it's increasing its height from the ground. And once the water starts falling, that gravitational potential energy gets converted to kinetic energy, right? And that kinetic energy then gets transferred to the rotation of these fan blades. But there is quite a lot of energy transformations occurring here too. Okay, so the water collides with the fan blades, imparts some kinetic energy there, but the water also falls to the ground, so it's not a perfect system. The moving fan blades then generate electricity. Okay, now we're going to look at the same scenario, but name the energy losses that occur. All right, well, first things first. When you have some kind of a heat source, some heat will be lost to the air outside the balloon. Okay, so a hot air balloon loses heat to outside air. So not all of the heat that goes inside the balloon stays inside the balloon. It will be lost to the environment. Okay, the heat from the bottom of the balloon, not all of it goes inside, right? So some of it goes outside the balloon and escapes from the bottom. The water that's falling, okay, it's not falling through a vacuum. So whatever gravitational potential energy that's stored, not all of that gets converted to kinetic energy. There's air resistance. Okay? The falling water continues past the blades and hits the ground. So not whatever kinetic energy it had after losing air resistance energy, whatever energy it had after hitting the blades, not all of it gets, well, imparted. Some of it still falls to the ground, some of the water. So that is energy loss as well. Internal friction. So this thing is rotating, but you have two pieces of solid rotating and moving against each other. That's going to be friction. Okay, so that's impeding the rotation. Now you're generating electricity. Okay? When you have electricity, the electrons are moving within the atoms of a wire. There's resistance, there's heat, so there's energy loss inside the wire as well. Now that last point here, it says the internal resistance generates I squared times R heat loss. So in grade 11, we would have seen that this is one formula for power. Current squared times resistance. But the idea is that you lose energy due to the electrons moving in the wire. So a lot of energy loss. Okay, let's look at the second law of thermodynamics and apply how that is, well, occurring in this situation. The second law of thermodynamics states that although it is possible to convert mechanical energy completely into thermal energy, it is not possible to convert all heat energy into mechanical energy. Now, if that sounds a little bit confusing, don't worry. Okay? It will make more sense once you apply to an example. Okay, so let's see, the balloon example. The balloon example demonstrates the second part of the law. Okay, the second part of the law says it's not possible to convert all heat energy into mechanical energy. Right? So the heat energy, which is coming from the flame, we're trying to make mechanical energy out of that. If you recall, mechanical energy is potential and kinetic energy combined. Okay, so it can be either one of them, but usually we look at it combined. So the heat from the bottom of the balloon, it allowed the balloon to gain height above the ground. It gave it potential energy, right? Which then the water gained that potential energy, converted it to kinetic. But not all the heat went into the system. Some energy was lost or wasted. Okay, so the first part, it is always possible to convert mechanical energy completely into thermal energy. That's true. It's always possible. Imagine you're kicking a box. Okay, we're not using the example of a soccer ball because the ball is going to roll much farther compared to a box if I kick them. Okay, so imagine you kick a box. It will slide across the floor and eventually come to a stop. So whatever mechanical energy you imparted onto it, excuse me, so you gave it some kinetic energy at the beginning, it moves with that kinetic energy, but there is friction between the base of the box and the floor, and that results in thermal energy, and the box eventually comes to a stop. Okay, so that's the idea of converting mechanical energy completely into thermal energy. But I can't just apply heat to this box and have it gain speed. So you cannot do this the other way around. Okay? If you do try to gain mechanical energy from thermal energy, there will always be some kind of energy that is wasted. Excuse me. All right. Now, while energy cannot be created or destroyed, it can change form. And sometimes, as we're studying, it's not changing form favorably. So the fact that it's not changing form favorably, we call that energy degradation. It's changing from one form to another and into a form that we don't particularly use, but it can also be changed into a form that we eventually need to use. Okay, finally we get to the Sankey diagram. Okay, so all of these energy conversions that are taking place, all of these energy losses that are occurring, we represent using a Sankey diagram. It's actually a really simple diagram and pretty intuitive. Okay, so consider the hot air balloon example. We start off with chemical energy. Okay, so either this is going to be from the wood or it's going to be from some kind of oil. There's chemical energy stored which can eventually produce heat. Okay, now that heat allows the balloon to rise up to a certain height. Okay, so it's gaining potential energy due to the chemical energy that it's using. Now, the water is also gaining that potential energy, which it's going to convert into kinetic energy. Okay? Now, the problem is there is energy lost there too, because not all of the potential energy gets converted to kinetic, like we discussed, because you have air resistance. Okay, so then the kinetic energy gets imparted onto the fan, which rotates. We get electrical energy. But again, it's not a perfect system. There's energy lost there as well, either due to the wires or due to the rotation of the fan shaft. Okay, so we see that from the beginning, the width of this ribbon keeps decreasing, decreasing, and decreasing. And you've got these yellow arrows. These yellow arrows represent the energy degradation loss. Okay. Now, you can actually write down energy values on the Sankey diagram as well. And so, for example, 100 megajoules of, we started with chemical energy, 80 megajoules of that got converted to potential energy. From that 80, 70 got converted to kinetic, and from the 70, 50 got converted to electrical energy. So overall, we went from 100 megajoules that went into the system, 50 megajoules came out. Okay. Now, we can actually calculate the efficiency of this process fairly easily. Now, if you look, we started off with 100 megajoules of chemical energy to get 80 megajoules of potential. Okay, well, you got 80 from 100. That's 80%. That's that one you can do in your head. Going from 80 to 70, well, this is your energy output, 70 megajoules. Your input was 80 megajoules. And so if you put it in this formula, you can figure out the efficiency. Although I don't think you really needed to see the formula. This is just common sense. Okay, so there's the efficiency for the first energy output, 80%. Okay, find the energy values for each of the degradations in the Sankey diagram. Okay, so originally we started off with 100 megajoules, and now we're at 80, right? So we lost 20 megajoules. Okay, the second time we go from 80 to 70, so we lost 10 megajoules. And finally we go from 70 to 50, so we lost 20 megajoules. Overall, we lost 50 megajoules out of the 100. Okay, the energy out has to equal the energy in. This is the law of conservation of energy. So if I take 50 plus 20 plus 10 plus 20, I have to equal what I had originally, which is 100. So what is the overall efficiency of this engine? Okay, so this was our hot water balloon water, hot air balloon water engine. So this efficiency goes from 100 to 50, that's 50% efficient. That's quite bad. But when you actually compare that to other engines, it's not so bad actually. Okay, so if you look at most gasoline combustion engines, they're on average 20% efficient. If you look at a hybrid car, they're on average about 36% efficient. So actually our hot air balloon water engine is pretty efficient, 50%. Okay, let's look at some efficiencies of various machines. Steam locomotive, 5 to 10% efficient, not that efficient. Human muscle, 20 to 25% efficient. Okay, we'll look at what that means in the next slide, but with reference to other organisms. Automobile, less than 25%, that's what we were just talking about. A compressor, 80%. And so if you're not familiar with what a compressor is, air compressors, it's essentially a machine that forces more and more air into some kind of storage tank. Okay, so that increases the pressure inside the storage tank, and eventually you can use that pressure into kinetic energy. Electric motor, 70 to 95% efficient. So that's pretty good. Okay. Now, living things, like you saw on the previous slide, human muscle is 20 to 25% efficient. Okay, all living things and all living processes are very inefficient. So we're going to consider the following case. Okay, you have a caterpillar. Okay, the caterpillar eats plant material. Okay, so let's say it obtains 200 joules of energy from that plant material. So where do those 200 joules go? Okay, well, I know that 100 joules of it goes to its feces. Okay, 33 joules goes to its growth, and 67 joules goes to something called cellular respiration. Okay, so those of you that didn't study biology, that pretty much just means it's gaining biochemical energy from its nutrients. Okay, so this is its energy, this is its change in mass, and this is its excrement. What is the caterpillar's overall efficiency? Well, we measure efficiency based on how much the caterpillar was able to grow based on how much it consumed. Okay, so it was only able to grow, only 33 joules of energy went into its growth from 200 joules. So we calculate the efficiency as 33 divided by 200. So the output is 33, the input is 200, producing a very low efficiency of 17%. Okay, so again, not an efficient process. Now let's look at the big picture. Okay, let's say you have 1 million joules of sunlight coming in. So for every 1 million joules of sunlight, this is what is effectively happening. Okay, so 10,000 of those joules actually goes to the primary producers. Okay, so for example, your plants. Okay, from that 10,000 joules that the plants are receiving, when the insect goes ahead and eats the plant, there's only 1,000 joules that goes to the insect. Okay, then what eats the insect? Your secondary consumer. Okay, from the 1,000 joules that the insect is getting, only 100 joules of that energy actually makes it to the secondary consumer. And then from that 100 joules, the tertiary consumer only gets 10% of that, 10 joules. So this is a very, very inefficient process. So note that in each stage, 90% of the stored energy is lost to the environment. So it's quite substantial. The last slide we're going to look at today in this video is the following. Okay, so this is an energy diagram for the United States. So from left to right, we're looking at how the energy is flowing. Okay, so on the left, if you look at this almost like a column, we can see all of the different types of energy. We've got electrical imports, that's about 0.08%. Nuclear energy, that's 8.1%. Hydro, 2.6, biomass, other, 3.2, natural gas, 19.6, net imports, 3.6, coal 22.6, US petroleum 14.9, and other imports 24.3. So overall, I mean, we've got 100% of energy coming in here on the left, and I mean, there's a lot of things going on. Maybe you can spend a few minutes to take a look at this diagram in more detail, but you can see that there's different uses of this energy. There's residential, there's commercial, industrial, there's transportation. Overall, the big picture here is that with all of these different types of energy coming in, whether domestic or imported, over half of that energy is lost, 56.2%. Only 35.2% is useful energy. Okay. So I'm going to stop there for today. So that is the end of 8.1 Energy Sources, video 1 of 4. Stay tuned tomorrow or next day for 8.1 video 2 of 4.